Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on the subject of computer science, and we are discussing the paper data structures. In this module, we are going to look at yet another multi-way search tree, which is called as B trees. Just like we had looked at different multi-way search trees like 2-3 trees, 2-3-4 trees, we are looking at B trees. When we were discussing 2-3-4 trees, we said that it is the basis for B trees. So, B trees is actually instead of being a 4 degree multi-way search tree, this is an M degree, it could be any degree. There is some other differences also, we will talk about that as we go along. These are the people responsible for the creation of this module, and these are the learning objectives of this module: to understand the concept of B trees, to discuss insertion into B trees, to describe the deletion from B trees, and then to discuss the use of B and B plus trees for indexing, and the keywords here are multi-way trees, indexing, redistribution and merging. So, let us go one by one. So, B trees, as we already told you, B trees are multi-way search trees. So, we know the property of search trees, commonly used in databases or other applications where we want to store a large number of keys. Not only that, we want to maintain the indexing in the main memory and have the actual key stored in secondary memory. We will describe that as we go along. And where a data is stored externally on disks, and keeping the tree shallow is very important. Keeping the tree shallow is very important because that will be in main memory. Each node takes one full, normally a node takes one full page, for example block or line of memory. So, that you know the page read, block read and those type of operations. This is to see the efficiency of memory operations. So, this is important. So, this is a B tree that is directly a data structure that is directly applicable to databases where the memory operations and the efficiency of accessing those things are important. Now, now let us go to simpler B trees first. Now, we have already seen B trees. If you say B trees is M way, then we have already seen there are two types already. The first one was 2-3 trees. It is a B tree of order 3, and each non-root node has 2 or 3 subtrees. And then we already seen 2-3-4 trees where it is a B tree of order 4, and each non-leaf node can have 2, 3 or 4 subtrees. So, this we have already seen. So, what we are trying to say here is these are nothing but simpler types of B trees, if you call them B trees, but they are normally not called B trees, they are called as 2-3 trees and 2-3-4 trees. If you have order 5, it will be called probably 2-3-5 trees. Okay. So, now let us look at the properties of a B tree. A B tree is a rooted tree having the following properties. Okay. What is it? Every node X has the following fields. What are the fields? It has, it will tell you the number of keys currently stored in node X. So, it will give you n of x, the number of keys that is currently stored in node X, it will tell you that, and nx keys themselves are stored in non-descending decreasing order. So, that key 1 of x is less than key 2 of x is less than key 3 of x and so on until key n of x. Just like in 2-3-4 we had SML where S is less than M is less than L, the same here, but there we had only 3 values. Here you could have any number of values. Here we are assuming n values, n is the number of keys stored. Obviously, the number of children will be n plus 1. Okay. And leaf x, a boolean value, is true if x is a leaf and false if x is an internal node. So, just like we need to differentiate between an internal node and a leaf node. So, we are having a boolean value which gives a value of true if it is a leaf and false if it is a internal node. And each internal node also contains obviously nx plus 1 pointers to children. The children can be C1 of x to Cn of x plus 1. So, here we are just generalizing 2-3-4 tree, that is all. So, what are we saying? Each node has the following fields. It tells you the number of keys in that node, okay, and the keys themselves of course ordered in a ascending order such that key 1 of x is greater than, is less than or equal to key 2 less than and so on. Leaf, it also gives an indication of whether this particular node, a flag, telling you whether it is an internal node or a leaf node. And then you have obviously each internal node alone, of course the external node or the leaf will not have. Each internal node will have how many pointers? It will have 1 plus the number of values. So, it will have nx plus 1 pointers to the children, where the children are C1 of x, C2 of x and so on up to nx plus 1 children. There will be pointers to those children. So, this is the concept of a binary tree, where each root is noded has the following each node has the following properties. All leaves have the same depth, which is the tree's height. This is again the same property that we discussed in 2, 3, 4 generalized. So, all the leaves of the B tree will be at the same level and that will be the height of the tree. Now let us look at the bounds on the number of keys of a node. There are lower and upper bounds on the number of keys a node can contain. These bounds can be expressed in terms of a fixed number t is greater than or equal to 2, called the minimum degree of the B tree. Okay. So, we are going to place this is something. So, every node other than the root must have at least t minus 1 keys. Then root has at least 1 t children. If the tree is non-empty, the root must have at least 1 key. So, what we are trying to say here is like in a 2, 3, 4 tree, you did not allow less than 2 children to be there. Here we are assuming that we are placing a bound on the lower and upper values. The first thing we are talking about is the lower value. Now, we are saying that a fixed integer t which is greater than or equal to 2. So, in the 2, 3, 4 and 2, 3, 4 the t was 2. Here it need not be 2, it can be more than 2. So, t is greater than or equal to 2, called the minimum degree of B tree. The maximum degree of B tree is B, okay, I mean some maximum. Here we are talking about the minimum degree. So, in the previous case we did not talk about the minimum degree because it was 2. Here it is not necessary to be 2, it can be some t. So, every node other than the root must have at least t minus 1 keys, and then the root must have at least t children if the tree is non-empty, or if it is empty non-empty, the root must have at least 1 key. So, that is the value we are seeing. Every node can contain at most 2 t minus 1 keys. So, the at most is also decided. Okay. So, for example, t is equal to 2, then 4 minus 1 3, that is what we are saying. If t is 5, then 10 minus 1 9 keys. If it contains 9 keys, it can have 10 children. Okay. So, we are saying the number of keys can be, let us say t is equal to 5, the minimum will be 5 minus 1 4 and the maximum will be 2 into 5 10 minus 1 9 keys or 10 children. Therefore, the internal node can have at most 2 t children. We say that the node is full if it contains exactly 2 t minus 1 keys. A node is full. Remember, we had a node full when it was 4. Here we are saying a node is full if it has 2 t minus 1 keys. There we said 3 in 2, 3, 4 node. So, this is the condition. Again, I will just repeat. Let us take the case of let us say a 10 way tree. We have 4-way tree, 3-way tree. So, 10-way tree. When we have a 10-way tree, t, let us assume t is equal to, if it is 10-way, that means 9 children. So, for t is equal to 5 basically. So, that is what we are trying to say. So, it is between 5 and 10. Why is this necessary? So, that we ensure that the tree is as shallow as possible. We will come to that. So, let us take an example here. Here the keys are ordered so that k1 is less than k2 is less than so on, and we have m minus 1 keys here and we have m children. So, each non-law of internal node of a B tree has between, this is the difference between what we spoke about in 2, 3, 4 tree, though it actually satisfied this property because 3-way tree had 2 children minimum and 4-way had 2 children. So, it satisfied this, but here since it is general, each node internal node has between m by 2 and m children and up to m minus 1 keys. So, it can have up to m minus keys, that is the number of children can be m. So, this is what we are trying to say, and keys are obviously ordered as k1 is less than k2 is less than and so on k m minus 1. Now, Now, let us take the keys k1 to km minus 1 and the trees t1 to tm. Children of each internal node are between the items in that node, the values. Suppose you have subtree t k or ti, which is the ith child of the node. All keys of ti must be between the keys ti ki minus 1 and ki. That is, ki minus 1 is less than or equal to ti is less than or equal to ki. So, this is the and of course, k1 is the smallest key in T1, that ki is the smallest key in T1. All keys in the first subtree Ti is less than k1 and T1 is less than k1 and Tm is greater than km minus 1. So, this is the property. So, any key you take, all keys in the ki minus 1 is the smallest key in Ti and all keys in the first subtree T1 is less than k1, all subtrees in the last subtree Tm is greater than or equal to km minus 1. So, this is the property of the k, we are now making it general, it is an M-way tree. So, if you take an internal node, the internal node has I search keys and I plus 1 subtrees. Okay. So, m minus I minus 1 inactive entries also you can have. So, if it is an m, you need not contain everything, is not it. Similarly, j data keys L minus j inactive entries. So, this is what basically the node will look like this. Now, let us take an example of a B tree. So, a B tree of the order of m is equal to 5, the minimum entry is 5 by 2 minus 1, that is equal to 2 entries. So, each node can have a minimum of 2 entries and the maximum entry is 5 minus 1 4 tree. So, actually this is a 2 3 4 tree and minimum subtrees is 3 and maximum subtrees is 5 1 plus. So, this is an example. So, you have the root, you have the maximum entries, you have the minimum entries and you have 4 entries for 5 subtrees. So, this is the idea of you have 5 subtrees. So, it is not a 2 3, it is a 2 3 4 5 subtree tree. So, the it is a 5-way tree, but this is a so that is why m is equal to 5. Now, in a tree B tree with m is equal to 4 and L equal to 4, so you have this as the example of that tree. As you can see, the number of nodes that you are maximum allowed to have is 4. Now, insertion, steps for insertion. If after inserting the node into the appropriate sorted order, no inner node is over the key capacity, the process is finished. So, if you have done an insertion and the number of nodes and the values in the node is less than the key, the maximum allowed, nothing has to be done, finished, insertion is fine. So, it is just insertion into a search tree, not binary, M-based search tree. If some node has more than the maximum amount of child nodes, then it is split into 2 nodes and each with minimum amount of children nodes and the process continues and then you take one node, split it up, put the parent up. If the parent does not violate, then finished, otherwise split the parent and keep going up. Process continues and the action is recursively to the parent node. So, overflow condition, a root node or a non-root node of a B tree of order n overflows if after a key insertion it contains m keys. M overflows m keys, order m, if you have, you can have only m minus 1 keys. So, if it has m keys, there is an overflow. Insertion algorithm, if the node overflow occurs, then split it into 2, propagate the middle key to the parent of the node. If the parent overflows, the process continues until you reach a parent that does not overflow. So, that is the thing. If there is no parent, that is you have reached the root, then you have to create a new node and complete the procedure root. In this case, the height of the tree increases by 1. Insertion of key always starts at a leaf node. So, you start with the leaf and go up. Now, deletion. In deletion in B tree, like insertion, deletion must be on a leaf node. So, if the key to be deleted is not in the leaf, swap it with either its successor or predecessor, each of which will be in the leaf. The successor of a key k is the smallest key greater than k. So, if it is a successor, the predecessor of a key is the smallest key less than k. Okay. Now, in a B tree, the successor and predecessor, if any of any key, is in a leaf node. That is the way it has been organized. We are not talking about how it is, we will just say so. Deletion must almost always be done from the leaves. So, let us see a simple deletion. Remove some key from the leaf and there are still enough keys in the leaf, so that there is no violation of the property m by 2 minus 1 keys, then you are done. Now, the removal of keys from the leaves can occur under two circumstances: when the key actually exists in the leaf of the tree, and that is the leaf itself contains the key, and when the key exists in an internal leaf and must be moved to the leaf by determining which leaf position contains the key closest to it. Okay. So, to the one to be removed. So, here there is a slight difference, let us discuss this a little more. So, the first condition is, if you have a node, I mean if you have a key you want to delete and it is in the leaf directly, and the leaf contains enough, it has a I mean even after you delete that key, it is satisfying the lower bound condition of m by 2 minus 1, then your deletion is done. But if you want to remove a key from the leaf, it can happen under two circumstances. The one we already spoke about, when the key actually exists in the leaf, or when the key does not exist in the leaf, but exists in the internal node. In that case, what you have to do is, you have to find a key that is closest to this, which will be the in order successor or predecessor. We will take one, as we already discussed, we will take successor. So, you just assume that that successor you find. Now, the leaf is in the internal node, the successor will be in the by definition of B tree, the successor will be in the leaf node. So, remove the leaf, the successor, the closest one, that will be removed, and then you will do the operation deletion, obviously replace it and then do the. So, what you do, take the leaf node, take it and put it in the successor position and then remove the successor. When you remove the successor, you have to do the deletion operation. So, locate the in order successor of the key to remove and repeat it with the key. If the leaf node is in legal state, that is minimum capacity is not violated, then we are finished. If some the inner node is illegal state, then because we have removed the node from there, then redistribute the siblings node, a child of the same parent node, and can transfer one of its keys to this particular current node. We have seen this in the 2, 3, 4 the same way, but this is much more generalized. So, redistribute the siblings of the node, that is a child with the same parent is called the sibling, and transfer one of its keys to the current node. So, that is what we do. Concatenate sibling does not have an extra. Now, all the siblings may not, I mean considering any of the siblings, none of them may have an extra key to share. In that case, both of these nodes are merged into a single node together with the key from the parent, and pointers are updated accordingly. The process continues until the parent remains in a legal state until the root has been reached. So, that is deletion. So, underflow condition is what happens. I mean deletion is basically about underflow condition. A non-root node of a B tree of order m underflows if after key deletion it contains less than m by 2 or it contains m by 2 minus 2 or less than m by 2 minus 1 keys. The root does not underflow. If it contains only one key, then this key is deleted and tree becomes empty. So, the deletion algorithm, if a node underflows, root the appropriate key from the adjacent left or right, basically sibling borrowing only. So, right or sibling, if the sibling contains at least m by 2 keys, otherwise perform a merging. So, there are 5 cases of deletion in a B trees. What are the 5 cases? The leaf does not underflow, then the leaf underflows and the adjacent right sibling has at least m by 2 keys. It should not have m by 2 minus 1, because then if you borrow it becomes less, I mean it violates the lower bound. So, at least m by 2, then perform a left key rotation. Okay. So, the right sibling contains more, left key rotation. The leaf underflows and the adjacent left sibling has at least m by 2 children, then obviously what you will do? You will perform a right key rotation. Okay, you do that. Now, the left underflows, I mean the leaf underflows, and each of the adjacent right sibling and the adjacent left sibling has at least m by 2 keys, both are possible, both have, then perform either a left or a right key rotation. Or the next condition, the leaf underflows and each of the adjacent siblings has exactly m by 2 minus 1 keys only, then perform a merging. So, only under this condition you will perform a merging. And So, those are the 5 cases that we saw. So, basically what we are trying to do, when a leaf underflows, you borrow from the sibling, okay, either the left sibling or the right sibling, and do the appropriate rotation. If both are can give, you can use either. If both have only exactly the number, then you cannot borrow. So, you have to do a merge. So, that is the 5 cases of deletion in B trees. And the runtime analysis of B tree operations. For a B tree of order m, each internal node has up to m minus 1 keys to search, and each internal node has m by 2 and m children between lower bound and upper bound. Depth of B tree storing n items is of the order of log of by m to n. So, runtime is approximately of the order of log m to binary search which branch to take each node, but m is small compared to n. Total time to find an item is of the order of depth into log m of the order of log n. So, now let us just go through the concepts of B trees. B tree insertion can cause expensive splitting, not only splitting, it can also propagate. So, if you have a tree of order 4, I mean depth 4, it could even propagate up to the root. B tree deletion can cause cheap borrowing, if you just have to borrow from the siblings, or expensive merging and deletion and propagation. Propagation is rare if both m and l are large, that is the lower and upper bounds. Repeated insertion deletion can cause thrashing, you keep doing this. So, if m is equal to l is equal to 128, then a B tree of height 4 will store at least, look at the number of items it can store. This is what is important as far as B tree is concerned. Okay. So, it can store 30 lakh items. So, let us look at B tree from the indexing viewpoint. Standard use index in relational database is a B tree index and allows for rapid tree traversal searching through an upside down tree structure. Reading a single record from a large table using B tree index can often result in a few block reads, even when the index and table are millions of blocks in size. So, whatever lots of size, even then only with a few block reads you can do, because the index has been stored in a very good efficient way. Any index structure then other than a B tree will be subject to overflow. Overflow is when any changes made to tables will not have records added to the original node's index structure, but will be tagged on to the end. So, that is the overflow, not the overflow we spoke about in B trees. So, what we do is, if there is an overflow, because in B trees we have left places where you can do insertion, when changes are made to the tables, they are put in the appropriate place and not attached at the end when we use any other data structure. That attaching at the end is called overflow from the database viewpoint. Now, so that answers our questions of why B trees for these. B trees are suitable for representing huge table residing in secondary memory, because with the large branching factor m, the height of a B tree is low, resulting in very few disk accesses. So, if you want each time you have a height thing, you have to access a disk. The branching factor can be chosen in such a way that the node corresponds to a block of secondary memory. You can choose it also appropriately, so that you just have to read, instead of having a value that you have to read 2 blocks for that way. And the most common data structure used for databases indices is the B tree, and index is any data structure that takes as input a value for a specific field and called a search key and quickly retrieves the actual records. Now, B trees are always balanced. Okay. B trees keep similar valued records together on a disk page, which takes advantage of the locality of reference. So, the locality of reference is taken care of by B trees, because all those records are kept in the same somewhat same area in the disk. B tree guarantee that every node in a tree will be full at least to a certain minimum percentage, and this improves space efficiently by reducing the typical number of disk fetches, which is what is the major idea that they use B tree for, in order to reduce the number of disk fetches necessary for any search or update operation. Now, let us go to a little bit of another thing, which is called as B plus tree based on B trees. So, insertion and deletion is log n, keep tree height balanced, f is fan out and n is the number of leaf pages, minimum 50% occupancy. Each node contains d is less than or equal to m less than or equal to 2d entries, which is what we spoke. The parameters d is called the order of the tree. So, this we have seen. So, supports equality, especially very good for equality and range type of queries, because they will be in the same place. So, what are the B tree characteristics? Data records are only stored in the leaves. Okay. Internal nodes store just keys. Keys are used for directing the search to the proper leaf. If a target key is less than a key in the internal node, then the pointer just to the left is followed, otherwise the one to the the target key is greater or equal to the key in the internal node, then the pointer to the right is followed. So, B plus tree combines features of ISAM, that is indexed sequential access method, and the B trees. So, that is what is called as B plus trees. It is implemented on disk, and it is likely that the leaves contain key, pointer points where the pointer field points to the record of data associated with the key. So, the keys are the ones that are stored actually, and allows the data file to exist separately from the B plus tree, which functions as an index giving a indication of where the data is actually stored. So, in this particular module we have explained the concept of B trees, we have discussed the insertion of B trees and we have deletion from B trees. More importantly, we have discussed the use of B and B plus trees for indexing. So, indexing as in database, how we use the memory, how we can design the B tree to suit the block size, and how we can use index in main memory and the actual records as keys in the main memory and actual records to be stored in the secondary memory, and so on. So, with this we have completed the balanced trees aspects of trees. So, we have looked at a number of balanced trees, 3 binary search trees and 3 more than binary. So, we saw a 3-way tree, a 4-way tree and a m-way tree, which is a generalized one, and we saw how it is really useful for actual applications. With that, we finish this module on B trees. Thank you.